Son of a scrub sucker. Ow! God damn it! Faulty Nimwatt converter. Circuit! No! Where's that new data pad? Get out of there, you rock crack. Okay, let's see what we got.
Incoming worm dispatch.
All right. Thank you, Eli, for that nice intro. Sam McMurray. Voice
So
of,
Serena wants Todd to work, just not for me.
right there, the voice of Todd, or I almost slipped there. The voice of Eli. Okay. So today is going to be a bit different. I'm actually going to cover one of the topics, the simulation topics that we have going on. Hi, welcome to the Verse. I am Christian Moe, the lead developer here at Tau City Labs. Yeah, we're making LithoBreak, a mining sim with a story-driven mining sim. I think it sounds like a very out there concept, but I think the result is pretty cool. Biased, maybe. So I just bring up my notes. I typed this like an hour ago. So yeah, we've got as you heard, Eli, voice acting by Sam McMurray. We've got a talented group of story writers, voice actors, artists, I guess me, the game development, programming, and simulation development. So part of what I bring to the table is my master's in mechanical engineering, and more specifically, my background in technical simulations, in terms of getting them not just working, but physically accurate, and also to a lesser extent performance, but definitely I've been honing in on that as we've been developing a game, because we need everything to run at 60 frames per second. Is my mic on? Okay, good. I did that 2 weeks ago, I think. Yeah. So part of that, and just excuse me while I exit.
Did my sister even show the kid the offer?
And I'm gonna get the AI, the old AI, to not.
Incoming worm dispatch from Janice at Cetus Tech.
Because I have some technical stuff to go over.
Janice. What are you up to today?
Okay, that should be good. So, where was I? Everything. Yeah, this stream will be all about the orbital mechanics of the game. It's going to get very technical. Sorry, not sorry. I think it's super interesting. I mean, our artist even finds it interesting, so I think others would find it interesting too. Everything in this game is actually part of a orbital mechanics simulation. So the station that we're on, we are orbiting that moon, which is orbiting that planet, which is orbiting that star, which is in a binary orbit around... Oh, where did it go? Ah, that star, too. I should not be able to hear the coffee from here. That's kind of cool. I'll fix that. Bugs. All right. So, our simulation, as it stands right now, is capable of hosting thousands of orbiting bodies at once on just modest hardware. This isn't very... I mean, this isn't trivial to do if you have a supercomputer, but you don't need that. But it's not trivial to do on, say a 5-year-old computer, which a lot of people are, playing games on, which we want to run on. So how do we do this? What is our secret sauce? I know you really want to know. That's why you're here, right? But before I go into that, I'm actually going to explain what an orbit is, and then it will become a lot easier to understand why we're doing it this way. So, this is where things can potentially go right off the rails. A whiteboard. I mean, is it a blackboard? They call it a whiteboard, but I don't know. Anyway, it's a whiteboard. I can doodle on here. You can see it. And I can make it a horrid mess. And it's for all the world to see. Right? Okay. So, an orbit is traditionally defined by 5 variables plus 1 variable as the position within that orbit. So we've got 6 variables. They will always be needed regardless of the solution that is implemented. So we need 6 variables to work with it. So keep that in mind, 6. I won't get into over-constrained and under-constrained issues here. Just know that 6 is our magic number. So traditionally, they use latitude of ascending node, inclination, and argument of perihelion to define the plane of an orbit. So you have kind of your... you got your XYZ, your normal XYZ, and then you kind of want to define a plane. So if all of these values are 0, you'd have a plane on the XYZ, kind of like that. But in this case, you have all of these 3 variables that will actually define the plane. Say it's like that, and this is our normal. So it's kind of coming off, let's just say the z-axis is off in this direction. So it's not in the actual z-axis of the game, which I should really be defining it like that, with our x, y, oh wow, and z. And then, our orbital plane is defined as a differentiation from that. And then our orbit is then defined as wherever that perihelion is, wherever that vector is, plus whatever circle that makes. Oof. Yeah, whiteboards and mouse drawing. This is great. But there's a problem with this. So we've got our... Okay, then they say that there's a perihelion, or semi-lattice rectum, I've seen it used, and an eccentricity. We're personally using perihelion or periapsis. No. Yeah, periapsis. And eccentricity, it simplifies a lot of the calculations down the road in terms of, simulating it. And then finally, the true anomaly defines that location. So like we have an orbit, but you can actually have like a position here. That's where you actually are in the orbit at that moment of time. And then you're moving along in that direction. Yeah. Okay. So let me just try and redraw this a little bit bigger for one. So we have our plane. We have our, center position. There would be a massive body right there. And then we have our orbit on that plane that we've defined that is different from the z-axis that we have, the normal z-axis that we have. Oof. So this is your x, your, let's say y, and then there's your z, kind of redefining here. And then that's your, then you'd have like a point here, and that angle would be your true anomaly. Oof. Then you have periapsis. If you're confused by all this, look up the Wikipedia page, and it's going to be a little bit different because, again, we're not defining it exactly how they are. But just know that we're just defining a plane, and then an ellipse along that plane, and then a position on that ellipse. So, plane, a shape, the ellipse, and position. The shape in this case is always going to be ellipse. It's a pretty quick mathematical solution. It does use some trigonometry in there, but more on that later. And same thing with the position. It's on that shape. However, this plane being defined is by 3 trigonometric variables. And that actually causes a bit of a performance bottleneck to the whole process. Whenever sine, cosine, tangent is called, a fairly computationally complex solution is employed to find the answer. This trigonometry is, traditionally what orbital planes are defined with. So it's 3 variables that are all angles. There has to be sine and cosine for each and every one to define the position, and it gets to be a pretty lengthy calculation. There's ways to optimize that, but there's ways to optimize the entire thing, which is exactly what we do. So these 3 angles are departing from a base orientation. So you might have like your orientation here, and then your base, your orbital plane is now a rotation, a deviation away from that normal position. So I just alluded to it's being a rotation, and that should trigger a few people to what we're actually doing here. So this is the optimization that took us from dozens of simulations with the old system to now thousands. I mean, just overnight. So instead of, defining it as, deviations rotationally, or almost like Euler rotations, sort of. We are using quaternions. And it's a pretty special case of quaternions. I'm just going to simplify this a bit. Just get rid of the XYZ. Let's just say this is Come on. Here's our center point. I'm just going to define an orbit. And then let's put a periapsis over there. So we use quaternions. And it's a special implementation that uses doubles instead of floats or singles. This is just so that we can get more accuracy, because we are calculating out at far angles and then rendering it at close angles or closer distances. So we need the accuracy in this case. But again, it's doubles in a quaternion instead of doubles in trigonometry. So it is way more performant. So remember back to the 6 special it's drawing a blank on me. I'm drawing a blank. But the 6 special variables, they're so now we are defining the quaternion is defining our plane and our, I guess, position. It's defining our rotation with 3 variables. And so it was 3 variables before, it's still 3 variables now. And then we still have the 2 variables to define the orbit shape, the periapsis and eccentricity, and then 1 more to define the true anomaly. So we are just as viable an option as the traditional method, but we have eliminated the need to calculate most of the expensive trigonometric functions. One caveat here is we are still defining the position with a true anomaly based upon trigonometry. We can't eliminate that, but we have literally 2 trigonometric calculations left when there were dozens before. And it's just a simple sine cosine. There's no tangents and cotangents being calculated. We can't eliminate that due to the shape of the ellipse, but again, a vast majority are gone. So we now have the I, J, K variables in the quaternion, periapsis and eccentricity, and true anomaly are 6 variables. So again, we are defining the rotation based upon a base location, just like traditionally. And then we draw our orbit shape on that plane with the, in this case, the z-axis on this plane is our periapsis. So like this is our z direction. And then our y direction is up from the plane, so it'd be about like that. And then x-axis, I need to do some mental rotation. Our x-axis is going to be this way along the plane. That makes sense? Yeah. 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 And then again, we have a point out here, and our true anomaly. I wish I had more colors. And then the eccentricity defines shape. Yeah, going on. And we move along in a counterclockwise direction, just like traditionally. So this is how we define everything, all the positions within LithoBreak. So we are slowly orbiting. You can see the sun is, or the star. I don't know if you're supposed to call it a sun or a star when it's in a different star system. Seeing it both ways. But everything is updating. In fact, it's this station that's really moving the most. The moons are moving, but they're a lot slower and rotating a lot slower, etc., etc. But this station is kind of setting the day-night cycle to be about, I think it was 6 hours. Was it 8 hours? Anyway. And that's defined based upon mostly just the mass of this moon and the distance away that we are in the rotation. So if we want to rotate slower, we would literally have to move the station further away so that our orbit is slower. And since we want to track the moon, because that's just, this view makes quite a statement when you're mining it. Yeah, we have the station rotation just physically matching the orbit of this moon, or its orbit of the moon. So now we get to play with oh gosh, telemarketers. Should have known. So I'm going to switch to a screen just like the whiteboard that you haven't seen before. This is our development environment. I'm going to just shut down the game so I have a little bit more resources on this computer available. Okay. Here is our development environment. You may recognize this. Oh well. Yeah, you can tell. Oh no, it's not even showing. Oh well. You can guess what development environment we use in our game. Where are my notes? Okay. All right. If there are any questions so far, I'm watching the chats. Yeah. We have viewers. Wow. Hi guys. All right. So this is our development environment. It is Unity. We use Unity. And this is we're renaming the free play mode into the interlude. It might change again, but this is, I'm just playing the game inside the development environment so I can switch some variables on you to kind of showcase how we implement this into our game. So I've already gone over how we make it way, way faster. Now I'm going to show, that yes, it is working, it is real. And yeah, first up is this little shuttle. It is actually updating in real time its orbit. It's changing its position. It's really changing its velocity so it can change its position. So it can track a point right off the station there. You'll see it overshoot. That's just because I want it to move faster. I could have it. Oh, anyway. Controls theory in game or in college. I could make it much more accurate, much faster. But I just let it overshoot for now because why not? So yeah. Oh, I thought I did. Okay. I guess go to the. No. So yeah, it's changing its velocity in real time, just tracking a point. And I'll prove that because I can just go and change that point. So you can see we've got the star, we've got the planets here, and here's the moon. Here is the shuttle. And it's actually, whenever I have this open, it does actually cause a bit of jitter to the orbit. You might see that. But just know that it's because there's back and forth going on between, the simulation and the editor. So with this, I will actually change the orbital close approach controller. That's what we got. And it should be position. We don't need those two. We just need to say, hey, I don't want you to be there. I want you to be... actually, we want it to be like positive 15, let's say. Yep, there it goes. So it is actually tracking a position in orbit in real time. And it's saying, okay, what do I need to do? Like what changes to my velocity do I need to make in order to move in that direction? And so this close approach controller says, okay, I need to change my velocity to point in that direction. But then it has to go and change its orbit. So we then have to say, okay, we've got this velocity that we're starting with, and we've got this velocity that we want to change to. We need to now update the orbit, calculate a new orbit every time it changes its... Every time it fires its thruster, it is literally calculating a new orbit. In real time. And like the game doesn't even hiccup, it doesn't even register that something is being calculated because it's so performant. That did not happen with the old solution. And I can even have this thing come real close so that we can hopefully see just how cool this looks. Allie did a great job in this. Yeah, come closer. Even down to 25. All this might overshoot. Come to the station. Getting close. Let me just move it a little bit that way. Maybe 1 more meter. Yeah. So yeah, this is just, I'm just changing where it should be positioned, and it's just going there. And it's calculating an orbit. That's kind of the cool thing, is it's not actually calculating its velocity. It's just calculating what velocity it wants to change from, and then the orbit gets calculated, and then it updates every frame depending upon the orbit, not depending upon some arbitrary velocity, relative to the station. And this is actually behaving itself really well, so I'm not sure if I fixed something accidentally. But you'll see, this orbit, we're on a, let's see. Oh, yeah. The station itself is on an exactly, 7, hold on. Yeah, 7 kilometers. Okay, we're 7 kilometers away. Gotta keep that in mind. No, 7,000 kilometers away. That's right. We are 7,000 kilometers away. But you'll see that this shuttle sim, even though it's really close, its orbit is actually a little different, just barely. And this orbit is changing so that it can stay just a little bit away from the station. But being a separate orbital body, it actually has drift and all of that Because if you put two objects like really close to each other in an orbit, they will actually start to deviate away from their starting position, just because they're technically on separate orbits. And that's what's happening here. Like, as this station rotates the moon, the station is literally rotating itself, and it is moving. So in order to keep a position, a shuttle would have to maintain its own position. So the next thing, wow, we're already at 30 minutes. I wanted to make these streams longer. I don't think I'll be able to make it. I won't be able to cover a topic like this every week, but I don't know, every month maybe. So the next thing we do, because we have more problems to solve, is how do we render everything? As I alluded to before, the rendering is using floating point precision for everything. The orbits are using doubles because we need to be able to simulate things out, to, like, this station is at 7 kilometers away from the moon. The moon is even further, which is already outside of the, it's actually, it's outside of the 40 kilometers that we can render with confidence, I guess. And then the planet is even further away. The stars are even further away. So we need to be able to actually take that double information and put it into a floating point precision without losing accuracy. And you can see, like, the star, if I can show the star's position updating, it's very smooth. And that took a little bit to do. So we had to move everything way close to the camera. So I will jump out to the scene view and actually show you what that looks like. So that moon, it looks like it's way out there because it doesn't move. It's actually tracking the position of the camera. But it is actually, like, what would that be? 200 meters? Well, I guess maybe like 1,000 meters outside the station. Like a kilometer out there. That's all. And then the planet is another kilometer out. The star is like 10. So everything's really close. And actually, yes, some of these planets don't have data assigned to them yet, so they look boring. I'll get some more. I'll get them, on their own inclinations and whatnot. So to show kind of an interesting effect of this, and this is kind of the trippy point, I'm actually going to update how we render. So you'll see that we have the simulation that actually sits separately from the orbital displays. We've got the orbital display that's for the camera, that's tracking the position of the camera. And then we have a separate one here that's using the same simulation information to update the positions of these holograms. So here's the trippy part. I can change all of these parameters so that some interesting things happen. So you'll see I'm like changing these variables and looks like nothing's changing, really, right? So there's your distance exponential. It doesn't look like it's changing anything, and that's the point. It looks exactly, except for that. Yeah, that's a little different. Oh, that's a little odd. Okay, there's a bug with close items then. Yeah, because it's trying to transition from one to the other. Huh. That shouldn't happen. I'll have to fix that. But anyway, for the most part, everything looks fine. I'll fix that one. However, I can change, say, this guy to, I think just, yeah. Okay. Actually, I think that's what I will do. Ah. It's been a while since I programmed in this. Oh, you know what? I think I know what it is. Alright, hold on. Come on. No. Okay, this is gonna have to be it. Okay. So, oh, so you can actually see that that's it's actually tracking the position of the camera now. And what's trippy here, just move that. Okay, you can go back away. Go away. Hi. What's trippy here should be, oh dear, what's going on? Oh, there it went. Yeah. So you saw it right there, that it was kind of starting to clip into the station. That's just the rendering itself. There we go. There, that's probably a good distance. But it's still, even at this distance, it still looks like it's way out there. Although we're having some glitches because I've got the inspector open on it. Oh wait, no, we're having some glitches just because it's rendering so close. Probably. But like when you back up, you can see that it's actually just rendering right outside the station, unless we come all the way back to the wall. Yeah. Let's put 4, 4, 5. So I can get it. So yeah, it looks like it's, well, what was that? What was I doing? That was at 0.4, right? What did I do? Oh, did I change the 2 scale render distance? Yeah, there we go. So yeah, even at this distance, because we're doing some funky stuff with the lighting, it still looks like it's way out there. But yeah, it's actually rendering not that far from the station. From the camera, actually. It's tracking the position of the camera. So yeah, I get some interesting shots going on. Oh, I thought, oh, okay, whatever. But yeah, that's how we render it. And then if I throw it back out to, yeah, 500, I see. That's weird. Alright. I programmed it. It should be weird. So yeah. We can see, like, if we have it at certain... We do have some improvements to make. One of them is to make sure that they don't elapse over each other. So when you're in the moon mining phase, it changes how it orbits, how it renders the orbits, so that it doesn't clip into the surface there. But that does show up, have a bug showing up, where this moon will actually get enveloped inside of the planet. I'll fix that. I'll fix so many things. I have so many things to fix. But anyway, it's game development. This is fun, really. So yeah, that's how we render. It's been a while since I programmed this. Just why it was a little finicky there to get that rendering anomaly to show up. But that's how we update the orbits, define the orbits, and render everything for LithoBreak. And I mean, we're going to use the tech in any game we make, probably. Any game that I can foresee us making. And this is just the tech that we're building up as we're building up this company, really. Because we want to make, with LithoBreak, we're covering topics like material science, engineering processing, thermodynamics we'll cover pretty soon here, chemistry. But those are just 4 topics I can name off the top of my head that we're covering. I mean, orbital mechanics, if you want to consider that one too. But that's really, I guess, physics. Yeah, there's 5 topics there. 5 topics that we're covering in one game. But there's a lot of science that we could cover. So, I mean, LithoBreak is going to be the game that we're developing for the foreseeable future. But we have ideas. Many, many ideas for the future. But yeah. So let's just go over some of the things that we are hoping to upgrade to the orbital mechanics. Right now we have the system that changes. Let me just bring that shuttle back. Where are you? There you are. Come back. I want you back. We have a system that can handle like close approaches and initializing an orbit relative to another object. So like if you saw the satellite that comes in at the end of the episode, it's actually initializing its orbit like out there, and then it's changing its orbit speed really quickly at like a couple Gs, or like I think it was like 1,000 Gs to make it come in really fast. Any human would not survive that, but if you harden a spacecraft to handle those sort of forces, it would conceivably work, especially with future materials. Hi. This shuttle is just, it's beautiful in my opinion. Yeah. Anyway. So, where was I? So it initializes its orbit. It changes its orbit, on close approach relative to another body, as long as it's within a certain distance. Then it can match that position. But what we don't have yet is a way to actually change your orbit, like do a high velocity change, unless we, kind of bake it in there with the satellite coming in. And what we want to be able to do is actually move materials from the station to the surface of this moon, and that moon, and that moon, and that moon, and all the other moons out there, using orbital mechanics, using the same calculations that we have. If you played Kerbal Space Program, now I know I shouldn't be naming other games as a game developer, but whatever. If you played these orbital mechanics simulation games, you'll know that it's not trivial to just know how to, go to another moon from one moon, or so in those cases a planet, to a moon, or to another planet, or to another moon on another planet, or on another planet. It takes some calculations, it takes some tools, and frankly, we haven't built in those tools yet to this game. But we will get there, and they will be based upon quaternion math, which, by the way, there's not really many research papers I know of that are using quaternions to define orbital mechanics, and then driving calculations based upon that. So it's not going to be like huge amounts of work, but it will be some work to make that happen. Especially since there's every single research paper out there and is basically calculating variables or values that we're not using. But we'll get there. So that's our plans, because we want to make this as realistic as possible. Again, it's a game, but I don't know. It's our game. This is what we want, and this is what we think that our players want. Frankly, we've never seen this in a game before, and we want to deliver something that's new. We want to experiment. We want to just, try to push ourselves. Because I have a master's in mechanical engineering. It took a lot of work to get that. And I don't know. I want to do something new in this world. Alright. So, that's what we've got. And, I mean, it's fun to geek out over this orbital mechanics stuff. It took quite a bit of work to get this working. But it was worth it. It's going to be something that we implement in our game. And if there's other games out there that want to implement this, join our Discord, talk to us. We'd be happy to. We're not going to just hand you our code. But if you have, some simple questions about how to implement this in your game. We're friendly game developers here. We've been helped out by the game development community ourselves. We want to give back too. So, we're here. So, with that, I think that's it. We've had a long live stream. Let's check the questions, if there are any. None so far. If there are any questions, I'll be on for just a couple more minutes while I wrap this up. And if you have any questions and you're watching this not live, head on over to our Discord, or leave a comment on YouTube, chat on Twitch, find us on Facebook if you want to, or Twitter. We're also on, or the Steam discussions. We're looking at those too. Anywhere else? Yeah. I'm sure some of you have my cell phone number, so if you just want to call me, go for it. Yeah. So yeah, I don't see any questions right now. No big deal. This is kind of evergreen content, so I'm going to be trying to do that more often instead of just updates. A weekly update about what we've been doing. Just more updates of what is complete, what's finalized. But again, that's not going to be every week. But if you ever see a live stream with a title, that's not just the date. That's a kind of evergreen. It should be a good view, regardless of when you're watching it. But with that, I think that's it. Stay safe in the verse. Maybe that'll be my sign off from now on. Who knows? Yeah, demo our game on Steam. Buy our game, please. And yeah, I'll see you next week.